Okay, so today we are going to talk about a new phenomenon, something called total internal reflection of light. Okay, what it means is that when light comes from a denser medium, let's say like something like water, into air which is less dense, then at some critical angle, after the incident angle is bigger than some critical angle, then the light ray will no longer penetrate the surface and go into the second medium, which is air, but it will be reflected totally internally. All right? Okay, so let me draw a picture and explain to you. So let's say this is a interface between water and air. This is air, and this is water. Just imagine you're holding a torch, a flashlight, and shining it towards the surface. It will go like that. And this is a vertical line. So this angle is the incident angle of theta 1, refracted angle theta 2, and so this is N1, this is N2. Okay? So to make it easy for you to understand, instead of writing N1, I'll write NA. Instead of N2, I'll write NW, right? So instead of N1, I'll write NA. Instead of N2, I'll write, instead of N1, I'll write NW. Instead of N2, I'll write NA. Okay? Same thing here. Instead of theta 1, I'll write theta W, the angle in water, and this is angle in air. Okay? Just change the name so that you can see. NW is usually about 1.33, NA is about 1. So we know that index of refraction for air is less than index of refraction in water. So let's write down our Snell's law. What is that? N1 sine theta 1 is equal to N2 sine theta 2. That is the one from coming from water. This is in air. So that is NW sine theta W is equal to N air sine theta air. We know NW is bigger than NA. This is sine theta A divided by sine theta W, just manipulation, just cross multiply. You got that. Now, NW is bigger than NA, so that's bigger than 1, so this is bigger than 1. What does that mean? That means sine theta A is bigger than sine theta W. That means theta in air will always be bigger than theta in W. Theta in water, theta in air is bigger than theta in water. So what does that mean? I increase this incident angle, which is measured, by the way, from the normal to the surface, a perpendicular line to the surface. So if you increase that angle, at one point, this refracted angle will be 90 degrees. That means this will be going parallel. Let me say it again. I increase this incident angle little by little, that refracted angle will go little by little getting bigger. So at one point, when it gets to the critical angle, then this refracted ray will be totally parallel to the surface. So in that situation, what you will see is like that. you have incident light ray coming at the critical angle, and this is the refracted ray, and instead of going into the other medium, it's now totally parallel to the surface, or you can say that the refracted angle is 90 degrees, right? So all you have to remember is that at the critical angle, when this happens, then the light ray is refracted the refracted angle is 90 degrees, or it's just parallel to the surface. So in this case, the refracted angle theta A will be 90 degrees, okay? Now, if you increase that angle, the incident angle, even more, what will happen? Well, if you do that, then instead of going to the other surface, then what will happen is, to the other medium, what will happen is that light ray will just reflect, obeying the law of reflection, right? Incident angle and reflected angle, okay? So that's what will happen. This angle, beta I, is bigger than the critical angle. So here, theta I is bigger than theta C, right? So that angle here, something like this. So this phenomena is called the total internal reflection. Just to remind you, when you have a situation like this, actually there's always some light going through the surface and something reflected back, right? But once you pass a critical angle, everything will come back in, and that's what we call the total internal reflection. So how do we use that? We use it all the time. We use it in telecommunications, computers, in light pipes. You have seen it. Probably if you walk through the mall, you will see those little fiber optics or fiber wires coming out. You know, glass pipes. Okay, you put light on one side, and then you have all the beautiful colors coming out from the other end, and they are called light pipes or fiber optic cables. You can call anything you like, but they are used every day. You also use it for computers. You also use it for medical purposes. For example, like somebody has a problem with the insides, the doctor has to need to look at their inside, and they do something called endoscopy, and then they use these pipes, put a little camera there, and then you can see the image, what's going on inside, right? So how they do is very interesting. Actually, I draw a very big pipe. Of course, the real light pipe is very small. And in real life, they could put some coating outside, but I'm just going to do that. So this pipe, inside is glass, outside is air. So we know air has less, smaller index of refraction than glass. So when you have a light ray comes in, it'll do total internal reflection, and it'll go like this, right? So it'll keep on going like this, right? And that's how you guide the light through this pipe, right? So actually, I mean, there's a lot of practical uses, right? Now, another thing that you can use this total internal reflection to explain is what you already, you know it all your life, something called rainbow. You know what a rainbow is? So let me explain to you briefly. Let's say this is the sun, and you are here, and you are facing in that direction, so that's your nose. So this is the sun, and then this is your line of sight in that direction. Then you will see a rainbow like this, right? So that will be the circle, center of that circle. And the angle you will see is approximately about 42 degrees. Then, from that line of sight, you look up 42 degrees, you will see a rainbow. You can do it at home with a garden hose, put the sun in your back, and then spray water in front of you. You can see that. All right? So what really happened is this. There are little raindrops here, everywhere, and the sun is so far, all the light rays coming from the sun, they are all parallel. So let me exaggerate and draw a big circular sphere raindrop, right? And just imagine that light rays come in, right? A light ray comes in. This is a perpendicular line. So then it'll go like this. Then it'll do total internal reflection, right? So it'll do total internal reflection. So it'll go like that. So that the incident and reflected angle are the same here. Then it'll come out. So that's a perpendicular, let me draw a little perpendicular, it will come out. That's one ray. Now, this is the red ray, let's suppose, right? Then I'll draw the blue one. And the blue one, if you remember, let's say if you have a prism, and the light ray comes in, light ray comes in, I'll draw a light ray with black ink. Then the red one goes like that. And the blue one goes like that. Right? So blue one get refracted more. Okay? So here, what will happen is, this is the light ray, which has, like all frequencies in here, all colors. Then once it enters the raindrop, then it'll go like that. Right? Then there'll be so that's what's happening in one little raindrop, right? Now the thing is, you'll see that the blue color is at the top and the red color is at the bottom, right? But actually, when you see the rainbow, you see the red one is at the top. The red one is at the top. And the blue one is at the bottom, right? The violet one is at the bottom. In between there are other orange and green and stuff like that, right? So that's what will happen. Right? The red one is at the top, the violet one is at the bottom. So what really happened is, actually, there are many raindrops, and so in this one, right, let's suppose there are raindrops here, then you are here. Some of them actually light rays that only that enter your eyeballs, right, that you can see, right? So actually what happened is that the red one that is going, so I'm going to draw the red one here. The red one that goes through like this is coming to you, and the blue one is coming to you. So just because the angles are right, then you see that the right one is the one that you see. Actually, in this one, the blue one is going out, and it's not entering your eyeballs, right? And in here also, the red one is not entering your eyeballs, right? So only these guys are coming to your eyes, right? So you can look in the book. The book has a much better picture. But anyway, so that's an explanation for rainbows. Then people have seen double rainbows, and actually double rainbows are triple rainbows. See, double rainbow is when you have two double internal reflection, right? So what happened is, first of all, it will refract, then it'll have one reflection, then it'll have two reflections, then it'll go out. You see? Okay? So single reflection, double reflection, then it'll be going out refracted again, right? My angles might be wrong, but the thing is, double rainbows are formed because of this, right? And triple rainbows is 3 times total internal reflection. So if you see multiple rainbows, actually the highest they have seen is up to 5, okay? But anyway, so you can read it on Google, you can read it in your book, but actually that's a brief explanation of how rainbows are formed. All right, so now let's do a problem example, and that is example 25.4. Okay, it said that find the critical angle, that is theta c, for polystyrene with index of refraction n is equal to 1.49. That's for polystyrene, and I want to find that. What does that mean? Means like this, and air, right? And air is 1. Polystyrene is 1.49. So you have polystyrene here, so that's NP is equal to 1.49, and air is equal to 1. And you want to find the critical angle. What does that mean? Critical angle means that the incident ray is coming in at such an angle, this is your critical angle, that the refracted angle will be 90 degrees and the refracted ray would go along the surface. So we want to find out what this is. And we have only one law, that's Snell's law. Snell's law said N1 sine theta 1 is equal to N2 sine theta 2. Incident medium N1, which is NP, polystyrene, sine theta 1, we want it to be critical angle. N2, which is N air, sine theta 2, what is theta 2? Theta 2 has to be 90, as I just explained, right? So, now let's put in the numbers. So, NP is 1.49, and then sine theta c is equal to NA is 1, sine 90 is 1, so right hand side is just 1. So that means sine theta c is equal to 1 divided by 1.49, which is 0.671, 0.671. You put it, make sure you put it in angle, degrees, not radian. Then your critical angle is sine inverse. You have an inverse function, 0.671, and the answer comes out to be 42.2 degrees. That means this angle for polystyrene will be 42.2, then the refracted ray will just go parallel to the surface. If the incident angle is any bigger, then it will be totally reflected back. Alright? Okay.